Hey guys, this is notes number 1 for polar functions, okay? Go ahead and write down this FLT here. And we'll go ahead and get started. You will need your graphing calculator just to show you how that would work when we're dealing with polar. But here we go. Like, what is a polar equation, right? You want to know how the graphing works and how can we apply what we know about polar and incorporate it into what we've been learning so far with like slope and area in calculus, right? So it's just a little extension of what we've been learning in calculus, but how do we extend that to or towards polar equations, okay? So what is a polar equation? So you guys have actually been dealing with polar equations before. It is another form of a parametric equation where you have different variables dependent on another one. So, for instance, when you were dealing with the unit circle a long time ago, your x and y coordinates represented the trig ratios to angles, right? So we had angles that were based on x and y coordinates and vice versa. So it is another form of parametrics, but the way you would find slope and area is a little bit different in a sense, okay? Because you're dealing with different variables. But anyways, this first part, I want to show you something that you may not have seen in IM3 or in pre-cal. Usually this part is omitted because they'll always say the BC teacher can take care of it. And here I am. So basically, you want to know how to graph polar, okay? And it's a little bit different from what you guys are used to. So, just to recap, if I were to ask you to plot 4, 3 on a rectangular coordinate, you guys were taught that the first coordinate, x, tells you to go left or right, and the y coordinate, the second one, tells you to go up or down. So in this case, we go 4 units to the right and then 3 up, and then we plot our point, okay? It's a little bit different when you're dealing with polar coordinates. Polar coordinates use r and theta. R stands for the radius, and theta stands for the angle, okay? So it's a little bit weird because you actually consider the angle first, and then you look at the radius second, okay? So it's kind of written backwards there, okay? But you think about the angle and then you graph your radius, all right? So before we can get to that, I need to make sure that we refresh on our unit circle, okay? So if you recall the unit circle, okay, these are some things that you need to know. There were quadrantal angles, okay? So we're only going to be dealing with radians here. So it was 0. And half a circle would give me pi, and a full circle would give me 2 pi. Okay? Half of a half circle is just pi over 2. And 1 1/2 is just 3 pi over 2. So you should somewhat recognize these angles in radian form. Okay? Every quadrant, quadrants 1, 2, 3, and 4, have the same relative 3 angles here, okay? So here's a refresher in case you guys forgot. You always got to remember that we're going in a counterclockwise motion. So we're going in this direction here, counterclockwise, okay? And then there are 3 angles. Pi over 6, pi over 4, pi over 3. And it oscillates. So 6, 4, 3, 3, 4, 6. 6, 4, 3, 3, 4, 6. This should look familiar, but if it doesn't, let me know. Okay? Now, the reason why they have very similar angles is because all of them are based on reference triangles. So you would still get the same relative reference triangle no matter which quadrant you're going to be in. Okay? Okay. The way it works here is if you guys look at a filled out unit circle, it doesn't look like this. You know, over here, it's not pi over 6, pi over 4, pi over 3. Okay? So there was a trick that I taught to my kids back in pre-cal or integrated math 3, but it depends on if you were exposed to it or not. Okay? So there's a pattern to it. If you guys take a look at the filled out unit circle, if you want to Google one, this first one here is actually 2 pi over 3. Okay, and you actually have to remember all of these angles. And the way you do that quickly is you notice there are certain patterns. When you're in the second quadrant, you notice that the numerator is always 1 less of the denominator, which is why if you think of 3, 3 minus 1 will give you the 2. Okay, so in this case, if you look at pi over 4, 4 minus 1 is just 3. So that's actually 3 pi over 4 there, okay? So think about what that would be there. Press play when you're ready. This is a no-brainer. 6 minus 1 will give you 5. So just know that when you're in the second quadrant, you subtract 1 from the denominator, okay? So I put a little minus 1 in the corner here. There's a pattern when you get into the third quadrant. You notice that the first one here is actually 7 pi over 6, okay? And that pattern there is that you actually add 1 from the denominator, okay? So that's 7 pi over 6. This one, if we're looking at 4, add 1, that would be 5 pi over 4. And figure out what that last one is there. Press play when you're ready. This one would be 4 pi over 3. So when you're in the third quadrant, you notice that the numerator is always 1 more, okay? Last one here is a little bit tricky. I'll give you the first one. This is 5 pi over 3. The pattern here is that you actually double the denominator and then you subtract 1. Double minus 1 there, okay? So if you take a look at this pi over 4, 4, if you double it, it's 8. If you subtract 1, it's 7. Okay, figure out that last one. Press play when you're ready. This one here would be 6 times 2 is 12, minus 1 is 11 pi over 6. So quadrant 1 is just pi over 6, pi over 4, and pi over 3. Okay? But the rest you got to know. So like, if I tell you 5 pi over 4, you should know that you're in the third quadrant because 5 is 1 more than the denominator of 4. Okay? So we'll practice that. All right, here we go. Let's take a look at part A, okay? Here's example 1. Write it down. Press play when you're ready. Okay, so when you're graphing polar coordinates, okay, you're looking at the angle first. So I'm going to go ahead and draw an X and Y axis here, okay? First thing you want to do is, where is 5 pi over 4? Okay? Press play when you're ready. 5 pi over 4, since 5 is 1 more than the denominator, it's a plus 1. So I know I'm somewhere in the third quadrant. Okay, so I'm somewhere here. All right, so here's what you do. Now you look at your radius. If it's a positive 1, you're going to go 1 unit out. Okay? And all of that is relative, right? Like, how do you know how far out to go? It really doesn't matter. Okay? But just know that you're going to end up right here. So this is 1 comma 5 pi over 4. All right? Let's try another one. So let's say I wanted to graph 2 comma 5 pi over 4. That would just mean that I'll use purple here. If I want to plot 2 comma 5 pi over 4, 5 pi over 4 is over here, but you're going to go twice the amount. So you're going to be somewhere over here. Looks a little bit weird. Okay, let's keep going. Here's part B. Okay, we look at 3 pi. Okay, now 3 pi is way beyond the 2 pi of your unit circle. So let me just show you how this works here, okay? That's 1 pi. That's 2 pi. And that's 3 pi. So you end up right here, okay? And since it's a positive 2, you're going to go out 2 units. So this right here is 2 comma 3 pi. All right? You're just understanding how this works, all right? But later on, you're not going to be expected to know how to graph it by hand, but it's good to know where it comes from, okay? Here's part C. Part C we'll do down here. Okay, so what you notice here is that your angle is actually negative. Negative just means that you go in the opposite direction, okay? So the easiest thing to do is you could either convert it to a positive, okay, or you cannot. So remember that, for instance, like this last one here, 3 pi, right? If anything is not in between 0 and 2 pi, you know that you can reduce it in a sense, okay? So you could always add or subtract some version of 2 pi to kind of reduce it. So for instance, in part B, when you have 3 pi, you could actually subtract the 2 pi because 3 pi is too much. And then you get pi, which is somewhere between 0 and 2 pi. Pi is actually right here. So 3 pi or 1 pi is the same thing. You end up in the same spot. It's kind of like when you spin in a 360 versus when you spin in a 720, you still end up in that same spot. Okay? So negative 2 pi over 3, what we're going to do there is we're going to add 2 pi to it. Because it's a negative, we want to turn it into a positive, all right? Because we want it somewhere in between a 0 and a 2 pi, okay? So when you add this here, go ahead and add it. You might need to recall how to add fractions, but go ahead and do that. Press play when you're ready. This is the same thing as negative 2 pi over 3 plus 6 pi over 3 if I multiply top and bottom by 3. And that would give me a 4 pi over 3. So negative 2 pi over 3 and positive 4 pi over 3 are essentially the same thing because you end up in the same spot. Okay? So my question to you guys is, where is 4 pi over 3? According to our unit circle, where is 4 pi over 3? 4 pi over 3 is somewhere in the third quadrant. So you got to know your unit circle, okay? So we know it's somewhere in the third quadrant. Okay, and we know we're going to go out 2 units. So we're going to go 1, 2. Okay. All right, let's do one more. Here's part D. Okay. Try this on your own. Press play when you're ready. It really doesn't matter exactly where you are. As long as you end up in the right quadrant, you're good. Okay, so 3 pi over 4, 3 is definitely 1 less, so I know I'm in the second quadrant, okay? So I'm somewhere here in that dot. But notice how the radius is a negative 3. Negative just means that you go in the opposite direction. So if you're in quadrant 2, directly opposite to quadrant 2 is quadrant 4, okay? And you're going to go 3 units in the opposite direction, Okay, so hopefully you've seen enough here. Let's run 2 more just to make sure. Here's part E. So if I did -3 comma pi over 6, try that one there. Okay, so pi over 6 I know is in the first quadrant. So I'll put a little dot there. Because the radius is -3, I know I have to go in the other direction. So the opposite of quadrant 1 is actually quadrant 3. So I'm going to go 3 units the other way. Okay, let's do one more just to make sure. Let's do -4 comma 5 pi over 3. Try that one there. Press play when you're ready. Okay, here, 5 pi over 3 I know is in the fourth quadrant because it's double the denominator minus 1. So I'm somewhere down here, but since the radius is -4, I'm going to go in the opposite quadrant, which is quadrant 2. So I'm going to go 1, 2, 3, and 4. So that's my point right there. And again, it doesn't matter exactly where you are as long as you're in the correct quadrant. Okay? So that's pretty much how you quickly plot points. Okay? Cool. So you guys have this unit circle, right? We had this unit circle where it was based off of reference triangles, where you had an x direction, a y direction, and you had your radius. This point right here represented your x and your y, but it was based off of what angle you were at. This is your unit circle. So you guys have been dealing with polar coordinates, you just didn't know it. Okay? So here's what we know. How do we convert, right? So how do we translate this language from rectangular, which is what we've been used to with x and y, to polar, which is r and theta, right? So there's a direct relationship here. I know that when I take the sine of theta, based on this picture here, what is sine of theta equal to? So it's been a long time since we've done trig, but think about that there. So remember that sine theta is opposite over hypotenuse. So in this case, the opposite is y. Across from the right angle is the hypotenuse, and right next to you is the adjacent, right? Okay, so I know that sine of theta here is really y over r. Okay? And I know that cosine of theta is really SOHCAHTOA, so adjacent x over hypotenuse r. This is how our unit circle came about. That's why the x-coordinate represented cosine and the y-coordinate represented sine for all of your ratios. Okay? So if I go ahead and solve for y here, if I multiply both sides by r, y will equal r sine theta. Okay? If I do the same thing here, if I solve for x, x would equal r cosine theta. Make sure that you guys have these two highlighted. Very important. This is how we convert from rectangular coordinates to polar coordinates. Okay? Okay, so there we go. That's what you guys just had. Make sure that it's bold and that you can recall it if you need to, okay? Okay, so when you're dealing with polar equations now, when you have an equal sign, right? How do you actually graph a curve? So just know that polar equations always start off as r equals and then something. So just to give you an idea of how it parallels, we always had the equation in terms of y, right? Y equals, and everything else was in terms of x, right? So same thing with polar coordinates or polar equations. Instead of y, it's r, but then all of your terms are going to be in terms of theta. So for instance, like r equals 2 sine theta. R equals 3 cosine squared theta. So everything will be in terms of theta in that sense, but r will always be isolated, okay? So different, but really the same thing, okay? Okay, so I want you guys to think about this here. What curve is represented by the polar equation r equals 2? So think about this here. We want to know what happens when we go around the unit circle, okay? So I want to know what my radius is when my theta changes, okay? So I'm going to use some very common angles. Let's do 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm using all of the quadrantal angles here. Okay. Okay, so based on this equation, r equals 2, okay, when my angle is 0, notice how there's no angle here, so that means my radius should be 2. So if my angle is pi over 2, it doesn't matter. My radius, according to this equation, will always be 2. Pretty easy to do, right? Okay, what if we were to plot this? What would it look like? Now, we could plot points in between, but that would take forever, okay? So let's take a look at just this first point. Remember, we look at theta first. So at angle 0, you guys know that you're over here on the positive x-axis, because remember, you open up counterclockwise, all right? So at angle 0 radians, you're facing the right. So the radius is 2, so you're going to go out 2 units. So 1, 2, and I'm going to make a point. All right? Okay. At pi over 2 is up top, and you're going to go in the same direction because 2 is positive. You're going to go up 2 units. So it traveled from here to here, okay? I'll do another one. At pi is towards the left here, and we're going to stick with the same direction because the r is a positive 2. Okay? So if you notice, there's a pattern to this. At 3 pi over 2, we're somewhere down here, and we're going to stay there because the radius is positive. And back to 2 pi. Whoa. Back to 2 pi, which is over here on the right, and we're going to stick with that same positive 2. So you actually travel. Oh, that was a bad one. You actually travel in that order, okay? Now, this is considered a function still in the polar realm, okay? Notice how if you look at this in terms of y and x, it doesn't pass the vertical line test, right? But in the polar world, every theta has a unique r, okay? Or every r has a unique theta, okay? So r equals 2 just means that regardless of the angle, your radius will always be 2. So if you think about that, it kind of maps out a circle, okay? All of that for a circle? Yes. So what you guys are going to do on your calculator, go ahead and turn it on. And really the only purpose of the calculator now, when we switch it to polar mode, it's strictly to look at the picture. That's all it can do, okay? So if you guys turn on your calculators, follow along with me here, okay? You're going to go to mode, okay? Right next to the second button, there's mode. And if you go down, you'll see the word function. And when you get to the word function, we're going to go ahead and change it to polar. So you're going to go to the right to polar, and then you're going to press enter. The only time you would want to change it to polar is if you need to see the picture. Okay? That is all. Okay? So if you wanted to calculate, you would have to go back to function. all right? So the only purpose to switching it to polar is to look at the graph, and that is it, all right? So go ahead and press second, quit. So when you guys press your y equals now, when you guys press y equals, you notice that all of them say r equals, right? That's how you can tell you're in polar mode. So for your R1, you're just going to write equals 2. We're just going to go ahead and graph that, okay? When you press enter, nothing happens. What am I forgetting here? R equals 2. Oh, there we go. R equals 2, you'll get something like this, right? And it kind of looks like an oval, but remember that your calculator isn't necessarily proportional. Notice how it hits positive 2s and negative 2s. So that's actually a circle, even though it doesn't look like one, okay? So you get to dabble with this, right? Like, go back to your y equals. And what if instead R1 was equal to 2 cosine theta? What would happen then? 2 cosine variable button, close. If you graph it, it looks like the circle kind of just moved over here somewhere, right? Okay. Now, what if we did, I don't know, 2 cosine of theta divided by 3. Let's see what that does. Okay, kind of like spirals, right? So you learn that there's all these weird different shapes. What else can we do that's popular? Let's do 5 sine theta. Let's see what that does. 5 sine theta, it looks like it's a circle, but it's just moved upwards. Okay, so you play with it, right? Here's one that you definitely want to try. Maybe 4 sine of 2 theta. That one looks pretty groovy. 4 sine 2 theta. Okay, it looks like a flower, right? But pay attention to, I can't even draw it. Pay attention to the path that it takes. It kind of looks like this. Shoot. Let me play that one more time. Okay, so it goes like this, like this, like this, and like that. And the path is actually very important, okay? So you get all of these somewhat symmetrical types of graphs here, okay? So you get an idea of how it kind of shapes itself. And I'll show you in this one example here. Okay, so you know what? We'll just take a look at this. Okay, so if we're looking at r equals 2 cosine theta, make sure you write that down, okay? Okay, so we're actually going to take a look at a lot of the angles in between 0 and pi here, okay? So I'll calculate the first few with you. So for instance, the first one here, this is 2 cosine of 0. Cosine of 0 is 1, and 1 times 2 is 2, okay? The next one, 2 cosine of pi over 6, I'll write it over here so we have space. Cosine of pi over 6 is radical 3 over 2. And if I multiply with 2, that just gives me radical 3, which is what I got right here. And I can go all day, all right? When you get to the second quadrant, cosine comes out negative because of the whole notion of all students take calculus there, okay? If I'm going a little bit too fast regarding the trig refresher, let me know. The reason why that comes out negative, well, there's several reasons why, but the easiest thing to think of is all students take calculus. It pretty much tells you what's going to be positive. So if you have any angle in quadrant 1 all trig functions will be positive, okay? Or all trig ratios. If you have an angle somewhere in quadrant 2, the only thing that's going to come out positive is sine, okay? And its reciprocal, okay? If you have an angle in quadrant 3 and you're dealing with tangent, tangent will come out positive. Everything else will come out negative. If you have an angle that's in quadrant 4, the only thing that will come out positive is cosine and its reciprocal, okay? So I know that since I was dealing with, where is it? Since I was dealing with 2 pi over 3, 2 pi over 3 is in quadrant 2, and I know the only thing that comes out positive is sine there. And since we're dealing with cosine, I know that it comes out negative. That's just a quick refresher there, okay? Anyways, let's plot these points because that's the whole idea of this, okay? So we have these points. I'll plot the first few with you, okay? So at angle 0, I'm on the positive x-axis, and I'm going to stay there because the 2 is positive, and that's where I plot my point right over here, okay? At pi over 6, pi over 6 is somewhere in the first quadrant, and I'm going to stay there because the radical 3 is positive, so I go out a distance of radical 3, which happens to be right there. Okay, let's keep going. At pi over 4, I know is in quadrant 1, and I'm going to stay there, and I'm going to go a distance of radical 2. Okay, so you keep going, and you notice how it kind of traces out the circle, but it's not like the circle where the center was the origin. It was kind of pushed out. And cosine tends to have this pattern. So, I mean, if you want to do some rapid fire graphing, graph 2 cosine theta for R1, and then do 3 cosine theta, 5 cosine theta, all at the same time, and you'll notice that there's a pattern. So I'll give you a minute to do that while I type it in as well. 2 cosine theta, 3 cosine theta, and 5 cosine theta. You notice that all of these circles are actually hugging on the right side on the positive x-axis, okay? So these are some common ones that you should remember. But anyways, this is our graph, right? Sketch the curve. Now, you won't be required to sketch, but we're just going to see what it looks like. So go ahead and type 1 plus sine theta in your calculator. On the AP exam, they will not require you to sketch by hand. Okay, almost always will they give you the graph. And in the case that they don't, you could always graph it on your calculator, okay? So this one kind of looks like a circle that got punched in on one side. It kind of looks like this, right? I believe this is called a cardioid, okay? But anyways, doesn't matter. This one here is pretty cool. This is the one I want to go over to kind of just wrap things up. I'm going to do this very quickly, okay? So when I plug in 0, I get the cosine of 2 times 0, which is the cosine of 0, which is 1. So I'm going to put 1 there. Okay? So I'm going to do the scratch work on the side just to show you guys. So the next one, the cosine of 2 times pi over 4, that comes out to the cosine of pi over 2. The cosine of pi over 2 is 1. Wait, hang on. Cosine of pi over 2 is 0. What am I saying? 0. It's the x-coordinate. Okay? I'll do one more. Cosine of 2 times pi over 2 next. That comes out to cosine of pi. And the cosine of pi is -1. So that's where I'm actually going to stop, okay? So if you notice, there's a pattern. And I specifically chose these angles, okay? It alternates from 1 to -1 and back and forth. So this one's going to be 0 and 1 and 0 and -1 and 0 and 1. I'm going to go ahead and hopefully try to plot this in order. So I'm going to use yellow here, okay? 0, 0 and 1. The angle is at 0. The radius, you stay there. So I'm going to be here. The next one is pi over 4, which is in quadrant 1, but the radius is 0. So I'm pretty much right here at the origin, okay? And there's a reason why I'm using different colors. At pi over 2, I'm at the top here. I'm at the positive y-axis, but since the radius is negative, I go opposite, so now I'm here. Okay? 3 pi over 4 is in quadrant 2 because it's 1 less. And since the radius is 0, I'm still back right here at the origin, okay? So you're probably asking what the heck is going on, but just follow my lead here, okay? At pi is at the left on the negative x-axis, and I'm going to stay there because the radius is positive, so I'm right here. Let's keep going. This darker green, 5 pi over 4 is in quadrant 3, but the radius is 0, so I'm back at the origin. Okay? Anytime the radius is 0, you're at the origin. Okay? At 3 pi over 2, 3 pi over 2 is down below negative y-axis, but since the radius is negative, I'm going to go opposite, and I should be up here. Okay? 7 pi over 4 is in the 4th quadrant, but the radius is 0, so I'm back at the origin. Okay? And at 2 pi, which is the positive x-axis, the radius is 1, so I'm going to stay there. Okay, so I have these colors listed, right? But it's important that you guys understand the order of it. So I'm going to use a doo-doo brown here. Okay, so we started off with yellow. And then eventually it curved to the orange. Then it goes to the red. Then it goes back to the pink at the origin. Then it goes to the green. Then it goes back to the darker green. Then it goes to the purple. Then it goes back to the origin. And then it goes back to the darker green. Okay? You guys can see this when you graph it on your calculator. It'll probably graph really quickly, so you kind of have to pay attention to it. So on your calculator, type out cosine of 2 theta. Notice the path that it's going in. Hit graph. The path is actually very important, so make sure that you guys pay attention to that. All right? You could probably zoom in because it's a little bit tiny to see on the graphing calculator. Anyways, that's my little bit on sketching. Okay? In other words, know how it works, but you're not required to sketch it by hand. Okay? Just know how it works. Okay, so one thing I want to go over with you guys is how do we incorporate it into what we've been learning, right? So we're just going to cover slope for today in this lesson, and then next lesson we'll cover area, all right? So remember that slope is really just dy over dx. The slope of a tangent line is really just the derivative, right? So here's what we're going to do. So just like parametric equations, what we're going to do here is we're going to take each differential, the dy and the dx, and we're going to go ahead and divide it by d theta. Okay? Because if we're in polar form, everything has to be related into polar, right? So what does slope mean in terms of the polar realm? Okay? So here's what we do. Okay? If we're just taking a look at this up here, okay? Let's ignore the denominator for now, okay? We're just looking at dy d theta. Remember, at the beginning of the lesson, y is equivalent to r sine theta. Okay? So what we're going to try to do is we're going to try to take the differential here of r sine theta. Or in other words, r times sine theta, okay? So here we go. This is a product. This is where you guys reinforce what you've learned back in AB. A product requires the product rule. So we take the first times the differential of the second. The derivative of sine is cosine theta. But with respect to theta. Okay, so first times derivative of the second plus the second times derivative of the first. The derivative of r is just 1, but with respect to r. Okay? Here we go. So then we want dy d theta, so we divide all of our differentials by d theta. You learned that d theta over d theta cancels out, and this is exactly what you have. I'm going to write it up here. This is really just r cosine theta plus sine theta dr d theta. Okay? So now let's take a look at the bottom, our dx d theta here, okay? Okay, so I know that from the previous part here, x is equivalent to r cosine theta. So I want you to actually pause here and figure out what dx d theta comes out to here, all right? Okay, so dx is equal to first times derivative of the second. Don't forget with respect to theta. Plus the second times derivative of the first, which is just dr. Then we divide our differentials by d theta, because that's what we want. So this is what we have now. This is negative, I'll just scoot the negative in the front, negative r sine theta plus cosine theta dr d theta. You will need to know this. Okay? Some people like to derive it so that they remember how it works. Some other people notice that there are patterns. So for instance, if you're more of the pattern type, notice how they both have dr d thetas. Okay? Top is sine, bottom is cosine. Okay? And then it switches. Cosine, sine. They both have r's, but the bottom one is negative. However you guys want to do this to remember it, do it. Okay? Personally, I just derive it just by doing that real quick. But if you feel like it'll be easier to just memorize it, then memorize it. Okay? Cool. So all of this here represents slope. Okay, so I'm going to show you how we use that in this one example here. All right. Write this one down, press play when you're ready. Okay, so we have this cardioid, 1 plus sine theta. That's the one where it kind of looks like a circle, but it got punched in. We want to find the slope of the tangent line when theta equals pi over 3. Okay, so here we go. We know that dy dx, I better hurry before this recording dies. Dy dx is just r cosine theta plus sine theta dr d theta all over negative r sine theta plus cosine theta dr d theta. Okay, that's what we just had, right? We want to find the slope when when theta is equal to pi over 3. So we're going to go ahead and evaluate this when theta equals pi over 3. Okay, so here we go. Now, what the heck is r, right? So we know that r is this. Okay? So that is going to be 1 plus the sine of pi over 3. That's my r, you guys. All right? Cosine of pi over 3 plus sine of pi over 3 times, and we'll come back to that derivative in a second, okay? All over negative 1 plus sine of pi over 3 times the sine of pi over 3 plus the cosine of pi over 3 times the derivative. All I'm doing is I'm plugging stuff in, okay? So the derivative, dr d theta, if you know that r is 1 plus sine theta, then you should know that dr d theta is just the derivative. The derivative of 1 plus sine theta is just cosine theta. Okay, so this is just, I'm going to go ahead and use a different color here. The derivative is really just cosine theta, but in this case, cosine of pi over 3. Cosine of pi over 3. And I'll kind of circle that just to show you, okay? Okay, and the rest is a lot of plug and chug. But you have an advantage. If you have a calculator, you can plug and chug, or equal is equal, right? Okay, so let's compute this real quick. So how can we do this easily? Okay, so I know, let me squeeze in another page here. Okay, I know that the cosine of pi over 3 is 1/2. So I'm going to plug in those 1/2s there. There's another cosine of pi over 3 there. Okay. Sine of pi over 3 is radical 3 over 2. So I'll plug those in. Okay, so I'm actually going to compute this on a calculator, even though it's super messy. And you guys should too. Is there any other easy way to do this? I guess not. Actually, you know what? I'll do this by hand. So if I distribute this, this is going to be 1/2 plus rad 3 over 4 plus rad 3 over 4 all over negative rad 3 over 2 minus 3 over 4 plus 1 over 4. Okay. Okay, up top, if I combine all that, that's going to be 2 plus 2 radical 3 over 4 all over negative 2 radical 3 minus 2 all over 4. Okay, just for the sake of time, this is so far so good, but I want to make sure that I end this video before this battery dies. We're just going to say that this is our answer, ANS, okay? This is our slope, okay? There was a part B to it. It says, find the points on the cardioid where the line is horizontal or vertical, okay? Where the line is horizontal or vertical. Okay, so, wait, what am I missing? Find the slope of the tangent line. Okay, so here, just to end it, think about what we had at the very beginning, right? We had all of this here. We had 1 plus sine theta times cosine theta plus sine theta times the derivative, which was cosine theta, all over negative 1 plus sine theta plus cosine theta, cosine theta. Okay, so if you want to find out the points where the cardioid, where the tangent line is horizontal or vertical, this is where you guys separately set each one equal to 0. If you want the slope to come out to 0, you're going to go ahead and make your numerator equal to 0. Okay? If you want to make your tangent line vertical, then you would make your denominator equal to 0. So I'll go ahead and do 1 with you guys, and then we'll end it there. So if we want the tangent line to be horizontal, we would set the numerator. That's a cool color contrast. Anyways, we would go ahead and set this guy equal to 0. Okay, I notice that I can factor out a cosine theta, and I'll be left with a 1 plus sine theta plus a sine theta. And that's enough for me to use the zero product property. So cosine theta is equal to 0, and 1 plus 2 sine theta is equal to 0. Okay, I would say the biggest hurdle here is that you guys are refreshing on your trig. So use this opportunity as a refresher, okay? If you maneuver this around, sine theta will come out to negative 1/2. So you ask yourself, when is cosine 0? And when does sine come out to negative 1/2? Press play when you think you have it. Cosine comes out to 0 at 2 angles, at pi over 2 and at 3 pi over 2. Sine comes out to negative 1/2 in quadrants 3 and 4. So I know it's going to be 7 pi over 6 and 11 pi over 6. Now, if you're not sure how I got those, this is where the refresher needs to come in. So just let me know where you are, and then we'll go from there. Okay? Okay, so in short, you learned how to graph polar. You learned that graphing polar is a little bit different than graphing rectangular coordinates, but finding slopes and such are, in a sense, the same thing, just found a little bit differently. Okay?